Hello, Chem 2. Today's fun-filled adventure in chemistry is some practice problems. A little different format today. We're going to go over 5 different practice problems, ones that I've had either on previous practice problem sets or ones that I found online that kind of made some points. And we're going to go through each one of them individually. I'm going to share with you the question, strongly suggest you pause the video and attempt it on your own, and then restart the video and watch the solution. So I'm going to give you the question and the solution. As I've said in the past, this format will do absolutely no good if all you do is watch the show. I've given the analogy in school of really liking watching pole vaulting, really liking watching curling or some sport. And watching it just doesn't cut it. You've got to practice. You've got to try it on your own to work out the kinks to see where your challenges are. And there's nothing wrong with going back and watching a video or watching a professional go ahead and solve the problem so you actually know how to do it. So let's get started. First off, administrative issues. First off, the gas law exam. I guess some of you were crunchy about due dates, considering I gave you a full week to do the gas law test. The complaint was from that, oh no, it's due on Monday. That's technically part of our spring break. We can't do that. I know we have a full week to do it, but we're going to have issues with it being due on Monday. So I'm going to move it to Tuesday at noon. So far, of the people who have actually taken the test, most people are getting perfects or near perfects on the test. So that's very good. So please get on there. I'd suggest in the next couple days, today's Wednesday, as I'm taping this, Wednesday or Thursday, go and get that knocked out so you're not having held over your head if you're truly going to be taking a spring break on Friday through Monday and then having to, in the time before noon on Tuesday, to crank out that test. You're not going to have a lot of chances to do it multiple times. So please take care of that as quickly as possible. And second, you guys have the homework or practice that I've already put on the OWL of the optional OWL and the required OWLs. The required OWLs are the ones that will go into the grade book once we get any guidance about what the heck a grade book looks like for the last marking period. Okay, let's get started. First question. First question is very atypical but slightly modified coffee cup calorimetry application problem. It says you take a piece of metal, and the piece of metal has a mass, and that piece of metal is heated up to 100 degrees Celsius. The way you normally do that is put it into boiling water for an extended period of time. Then you take that piece of metal that is at 100 degrees and you plop it into 100 milliliters of water. 100 milliliters is 100 grams of water. Remember, water has a density of 1 gram per mil. And then you're going to go ahead and plop it in there. That water starts off at 23.7 degrees, and you put it in, and the water warms up. The piece of metal obviously cools down. All the energy from the metal goes into the water, and the water's new temperature is 27.8 degrees Celsius. Question is, assume that no heat is lost to the environment. You are doing a true coffee cup calorimetry, a very well insulated container. What is the specific heat of the metal? What is the specific heat, the C of the metal? Go ahead and pause this video and try it on your own. Do as much as you can. I'll be back in a few. Okay, hopefully that went well. Let's see what I did. So first thing I tend to do is I tend to collect the information that I find relevant to this particular problem. And in this case, the problem was very clear to say that we have a 59 gram piece of metal and 100 grams of water. The metal starts off at 100 and the water starts off at 23.7, and then they finally get to a final temperature of 27.8. So I know that the Q of the metal is going to be the same amount as the Q of the water. The heat lost by the metal is going to be the same as the heat gained by the water. So the only difference is that there's going to be a sign change. The amount of energy is going to be the same, but the sign is going to be different. So Q metal equals negative Q of water. Both of them I have a mass, a change in temperature, and obviously I know what the C is for water, and I'm trying to solve for the C of the piece of aluminum or piece of metal. I think it's supposed to be aluminum here. So C is what I'm solving for, so I'm going to use MCAT for each one of these. So I set it up as MCAT for the metal equals MCAT for the water. And ultimately, what I'm going to have to solve for is the C of the metal. So if I take the C of the metal, divide both sides by the mass of the metal and the temperature of the metal, I get this equation. Negative mass of the water times the C of the water times the temperature change of the water divided by the mass of the metal, the temperature change of the metal. Plug my numbers in, and lo and behold, I get an answer of 0.4 joules per gram degree Celsius. Okay, so that would be the specific heat of this metal. That's actually pretty low. You'll see in a second as we do some other ones, but this thing is not aluminum. Okay, so there's your first problem. Hopefully that went really, really well, and that was fairly problem-free. Again, hopefully you did it beforehand rather than just watching the explanation. Next question. Next question is a bomb calorimetry question, but it has a slight, very, very slight twist. One of the things about these problems I want to share today is I want to make sure that I show you some different applications, ways that you can use the technology or the calculations that are involved in what we talked about in yesterday's video. So in this situation, we have a 1 gram sample of octane. It is a measurable quantity of octane. I've measured out 1 gram on a nice balance and put it into my bomb calorimeter. The bomb calorimeter has 1,200 grams of water in it, and initially the entire bomb calorimeter and the water has a temperature of 25 degrees Celsius. I allow it to explode, boom, bomb. After the reaction, the temperature of the water gets up to a really, really warm 33.20 degrees Celsius. I also know that the heat capacity of the bomb calorimeter, or the calorimetric constant, that's the metal and the container and all that stuff, is 837 joules per degree Celsius. Question is, if I assume the specific heat of water is 4.184, calculate the heat of combustion of octane in the units of kilojoules released per mole of octane. Kilojoules released per mole of octane. Go ahead and pause this video, try this on your own, and I'm going to be back in a couple seconds. Okay, let's see how you did. What I'm going to do here again is I'm going to click my variables, click my data. My octane was 1 gram. My water was 1,200 grams. The heat capacity of the bomb was 837. The initial temperature was 25, and the final temperature was 33.2. So this bomb actually did, bomb and the water both absorbed in a large amount of energy. So first thing I need to worry about is, what is my change in temperature? Well, my change in temperature is 8.20. That's how much the temperature of everything increased. That's not only the bomb, but the bomb and the water all increased in temperature of 8.20 degrees Celsius. I know the bomb. I'm going to use the bomb as being the entire contraption, the calorimeter itself and the water. The Q that is going to be absorbed by the bomb, that's the calorimeter and the water, is going to be the Q of the calorimeter plus the Q of the water. So I'm going to use CAT, big C, since they gave me the heat capacity, big C, for the calorimeter, times the change in temperature, plus I'm going to use MCAT for the water, since they gave me the grams of the water, and I know the little c, the specific heat of the water, and again, the temperature change is the same. I'm going to go ahead and use that equation for the water. So what I've done is here is take the heat that is absorbed by the bomb and the heat that is absorbed by the water and combine them together. Oops, I did this twice. Okay, so if I go ahead and do C times change in temperature plus C MC delta T, I get that I had a total heat loss, or a total heat absorbed by the bomb and the calorimeter of, what is that, 48,000 joules of energy. Okay, so 4.8 times 10 to the fourth joules of energy was absorbed. And that's only half the problem because the question asks specifically what is the heat of combustion of the octane in kilojoules per mole. So if I know the entire bomb absorbed 4.8 times 10 to the fourth joules, I know the heat of the reaction is the opposite heat of the bomb, so I know that's a negative. So the Q is going to be 4.8 times 10 to the fourth divided by the 1 gram of the material, the 1 gram of octane, since I'm trying to get it per mole. Convert that over to moles, convert that over to joules, and obviously I didn't finish this, so that is going to be in 5.49 times 10 to the 6 joules per mole. It actually asks in kilojoules, so it'd be 5.49 times 10 to the third kilojoules per mole. That's a lot of energy. Okay, let's try another one. Now, the next three are going to be a little all over the place, not a very specific to a bomb or very specific to a coffee cup, but using the concepts of both of them, using the concepts of calorimetry to solve some more unique, interesting problems, one of which is really kind of funny. Okay, next one. So I have, for this third situation, it is very coffee cup-ish. I have a 25.54 gram block of aluminum. It's warmed up to 65 degrees. It's plopped into a beaker of water that has a known mass, 55.28 grams, and it starts off at 22.2 degrees. They're allowed to come to equilibrium. Here's the question. Assuming no heat is lost, what is that final temperature going to be? So instead of the previous coffee cup calorimetry where they gave me the initial temperature and the final temperature, here I'm going to need to know what is the final temperature. I'm going to calculate the final temperature in the calculation. So again, go ahead and pause this video. I'll be back in a few seconds. Try it on your own. Pause. Don't cheat. Go ahead and do it on your own. You can do it. Okay, let's see how this problem is to be solved. So again, I'm going to collect my data. I have my masses, my specific heats, and my initial temperatures. What I don't have is my final temperature. I have no idea what the final temperature is. So what I need to do is I need to recognize that whatever heat change that happens to the aluminum, the same amount of heat change is going to happen to the water, but in an opposite direction. The water is obviously going to increase in temperature and the aluminum is going to decrease in temperature. So the Q of the aluminum is equal to the negative of the Q of the water. In both cases, I have an MCAT, MC delta T. So MC delta T for the aluminum, MC delta T for the water. Obviously, there's a negative sign in there. Now remember, delta T is temperature final minus temperature initial. Temperature final minus temperature initial. Delta always means final minus initial. So if I plug those in and change the format a little bit, I put myself in a better situation because I know that my final temperature of my aluminum and my water are going to be exactly the same. I have the mass of the aluminum, I have the C of the aluminum, I have the initial temperature of the aluminum, I have the mass of water, I have the C of water, and I have the initial temperature of the water. Essentially, I'm solving for one variable. So if I plug everything in, 25.54, 0.91, T final, 65.4, ... I plug in all my numbers to get everything pulled straight off the table, and then I distribute. So I take 25.54 times 0.91 times T final, and then 25.91 times 0.91 times 65. I get this relationship. Now, again, at this point, I've simplified things by saying, since I know my temperature final for both the aluminum and the water are going to be the same, I just put this in as T final. Push everything to one side, add 1,520 to both sides, and add 231.29 TF to both sides. I get this, and then solve for TF, and I find that my temperature, my final temperature, is 26.15 degrees Celsius, or 26.1, however you want to look at it. Again, I'm not going to stress over sig figs. If you go back and put that number in to these equations, which I did, you get two numbers that are really, really close to one another. Not exact, but very, very close to one another in the amount of heat loss and amount of heat gained. You got to be okay with the fact that you might be off by a smidge. Okay, so that's that problem. Your final temperature of your entire system is going to be 26.5 degrees. Makes sense. 22 degrees down to 26, and 65 down to 26. And the reality is, obviously, water has a much higher specific heat, so it is going to take a lot more energy to change the temperature of the water relative to changing the temperature of the aluminum. Next problem. Okay, so this is a funny problem. I found this one online, so if you want to absolutely positively cheat, you can go online and find it. It was kind of funny. I thought it was kind of an interesting way to look at things. Very similar to something that I like to look at, but it was a different version. It says, Phineas Fogg, a character who went around the world in 80 days, was very, very fussy about his bath water. It had to be exactly 38.0 degrees Celsius. You are his butler. One morning while checking his bath, you notice, oh my goodness, it's 42 degrees Celsius. You plan to cool down the 1,000 kilograms of water. Why you know the exact mass of water, I don't know, to the desired temperature by adding, here we go to the weird part, an aluminum ducky that was originally in the freezer at negative 24 degrees Celsius. What mass ducky should you grab in order to make sure this water drops from 42 down to 38? They gave you a specific heat of aluminum. We use aluminum in the last problem, and the density of water, you're reminded that is 1 gram per mil. And you are to assume that no water is lost to the air or to the tub or anything else. How big of a ducky, an aluminum ducky, should you add to this bath water in order to allow it to cool down to reach a thermal equilibrium that would be at 38 degrees Celsius? I'm going to go ahead and ask you to pause the video, try this one on your own. It is somewhat similar to the last problem in that the metal is going to be losing heat and the water is going to be gaining heat. Sorry, vice versa. The metal is going to be losing heat and the water is going, the aluminum is going to be gaining heat, is going to be going from negative 24 up to some warmer temperature, hopefully 38 degrees, while the water is going to drop in temperature from 42 down to 38 degrees. Go try this one on your own. I'll be back in a few seconds. So how'd you do? Did you get a pretty sizable aluminum ducky? Let's see how I did. So I collected the information. I don't know the mass of the aluminum. That's what you're trying to solve for. I do know that the water is 100 kilograms, which is equivalent to 100,000 grams. So just reminding myself here that that is 4 sig figs. The specific heat of the aluminum and water are both given. The initial temperature of the aluminum and water are both given. And I know that my final temperature, I want to be down to a very, very cool, actually, 38 degrees. Body temperature is at 37. That's just a little bit above body temperature. So I know that the aluminum's heat is going to be the same as the water's heat. It's just going to be moving in a different direction. The aluminum is actually going to be absorbing heat and the water is going to be releasing heat. So I do my MCAT on both sides, MCAT for the aluminum, MCAT for my water. The difference is the sign, the convention of the negative. And then since I'm trying to solve for the mass of the aluminum, I simply divide both sides by the specific heat of aluminum and the temperature change of the aluminum to get this configuration, this calculation. I'm going to go ahead and plug my numbers in. I know that my temperature change for my aluminum was 62 degrees plus. It's going from negative 24 up to 38 degrees. And my temperature change for my water is dropping only 4 degrees. So I plug those numbers in, get an answer. I need to have a 30 kilogram piece of aluminum in order to cool down that water bath. Think about that. I have 100 kilograms of water. In order to drop it just 4 degrees, I need to have a 30 kilogram piece of aluminum. That is huge. Okay, so how did you do? Did you come close to that answer? Did you do everything correctly? Did you make maybe a minor mistake, a more significant mistake? I don't know. Hopefully it went well. Okay, last problem is a relevant problem, a real world application I think is kind of unique to think about. This one actually is one that came off of what would have been a previous problem set. So you have a piece of chocolate cake. A piece of chocolate cake has 400 calories. Now, those are nutritional calories, 400 nutritional calories. And we know that a nutritional calorie is 1,000 thermochemical calories. How many, this is kind of weird, how many 8-inch steps must a 180-pound man climb in order to expel or expend the 400 calories from eating that piece of cake? You're going to go back to thinking in terms of physics. The formula for potential energy is mgh. So you're talking about how much energy you have to expend in order to get up. You have a mass, you have a g, which you should remember, but I gave to you. The g for gravity on this planet is 9.8 meters per second squared. And you want to find out what is the height. How high do you have to go? And how many steps do you have to go up in order to expel that amount of energy to make up for the cake? I'm going to come back to this problem in a few. Go ahead and pause this video, try it on your own, see if you can get the number of steps. Reality check, you got to walk up a lot of steps. I'm going to tell you that right now. You're going to walk up a lot of steps to wipe out that one piece of chocolate cake that's at 400 calories. Hit the pause button. So how did you do? Did you get a large number of steps like I did? Let's see what I did. So first thing I need to do is convert my food calories to joules so I can use my MC delta T and all that fun stuff. So food calories was 400. There's 1,000 thermochemical calories in a food calorie, and there's 4.184 joules in a calorie. So I need, oh my goodness, 1,673,600 joules of energy is in that one piece of cake. That's insane. Then, recognizing that my force times distance, or my MGH, I'm going to solve for my distance. Okay, my height is the work or the energy divided by the force. My force is M times G, or MA. So I have a 180-pound man at 0.454 kilograms per pound. And then 9.8 meters per second squared, I have 800 newtons of energy needs to be expelled by this person. He's going to be pushing down on the planet at a force of 800 newtons. So I'm going to take my energy that's in the cake, divide it by my amount of force, the 800 newtons, and I get there's 2,092 meters I have to go up. So if I take 982 meters at 3.28 feet per meter, 12 inches per foot, 8 inches per step, I need to go up 10,000 steps, 10,000 steps in order to expend the amount of energy that is contained in that one piece of cake. 10,000 steps, 8-inch steps going upstairs in order to do that. That's crazy. Anyway, so hopefully you found this to be somewhat helpful. Hopefully you did play along with the game of trying the problems on your own. I know the original video is going to be a little less than 25 minutes, but hopefully this took you a lot longer than that because you tried each and every one of these problems on your own. You didn't just watch the answers. What's next? Well, next week, what we're going to do is we're going to focus on this concept of enthalpy and thermochemistry equations and how that all connects together. How does heat connect with balanced chemical equations? How does the amount of energy loss and amount of energy gain connect up with a balanced chemical equation? We're looking at just another stoichiometric connection. This time, instead of looking at the amount of reactants or the amount of products, we're going to look at the amount of heat. And it is very, very quantifiable. So anyway, hopefully you guys are having a great day. As I'm taping this, this is on Wednesday. You guys have, again, remind you, you have that test to get out of the way. Most of you who have taken it so far have done perfect on it. That's fantastic. That's really going to help your grades for the marking period. Everybody out there, stay safe, stay healthy, practice your social distancing. Don't go too stir crazy. Be nice to your family. Be nice to your siblings. Don't drive your parents crazy. And phrase it pays. Always remember, never forget that sig figs do matter. You guys have a great day. I will see you hopefully sooner than later. Toodles.